Welcome to my project with Aqua Armour on the adhesive selection analysis for the Aqua Armour wetsuit. Shark attacks pose a constant threat to anyone participating in recreational and occupational marine activities. A total of 129 shark attacks were reported last year worldwide, with 8 fatal incidents occurring within Australia alone. Numerous prevention methods have been employed around Australia to reduce the risk of shark attacks. Shark nets are designed to capture, entangle, and kill sharks. They do not offer complete protection but work on the principle of fewer sharks, fewer attacks. Shark nets have effectively reduced the total number of attacks since their introduction in 1935. In Queensland, there has been only one fatal attack on a controlled beach since 1962. Compared to 27 fatal attacks between 1919 and 1961. However, shark attacks are also responsible for endangering threatened marine life. In 2018, 403 animals were killed in nets in New South Wales, including 10 critically endangered grey nurse sharks, 7 dolphins, 7 green turtles, and 15 great white sharks. Another prevention method used today are shark barriers. This is a non-destructive method which offers complete protection by forming a fully enclosed swimming area that prevents sharks from entering. However, shark barriers are not effective on surf beaches because they usually disintegrate in strong swell. Other prevention methods include shark tracking. This involves tagging the shark with an electronic device which warns lifeguards if a shark is nearby. Drones, helicopters, planes, and observation towers are also used to spot nearby sharks. All these methods help reduce the risk of a shark attack on patrolled beaches, but still don't provide a solution for unpatrolled waters. This is where Aqua Armour comes in. Aqua Armour is a wetsuit which aims to provide flexible, lightweight, and comfortable protection against shark attacks. It achieves this through the use of a flexible Kevlar protective armour, which effectively reduces the penetration depth of the shark's bite to ensure vital blood vessels and nerves aren't reached. A lycra top layer is placed on top of the protective material to improve the appearance of the wetsuit. In order to manufacture the wetsuit, a suitable adhesive must be selected to attach the protective material and the lycra to the neoprene. Relevant adhesives need to be tensile tested and fatigue tested to compare their strength characteristics for this application. Before mechanical testing can commence, the suitability of different adhesives needs to be compared. The adhesive must have a high resistance to salt water, as it will most likely be used in the ocean. The adhesive must also be able to withstand temperatures as cold as 10 degrees Celsius in cold winter waters and as hot as 6 degrees Celsius in cars on hot summer days. The adhesive must also be flexible to allow for stretching when the wetsuit is taken on and off, and be strong enough to survive loads from normal use. To lower the manufacturing time, a smaller cure time is preferred. Also, to decrease the cost of the wetsuit, a cheaper price is also preferred. These attributes were recorded in a matrix for multiple relevant adhesives, and the most suitable adhesives were selected to be tested. The tensile testing for the adhesive is to be conducted in shear because that is the most common loading scenario for the connection. There are 2 ways to test a joint in shear, the first of which is a single lap joint which consists of one piece of each substrate glued together, which are pulled apart in opposing directions through the use of a tensile testing machine. The second is a double lap joint which uses 2 pieces of the first substrate, each glued to either side of a single piece of the second substrate. The single lap joint induces a secondary bending moment because the forces aren't centered. The double lap joint, on the other hand, doesn't produce any secondary bending because the forces act through the center of the joint. Therefore, the double lap joint is a superior selection to ensure the joint is loaded purely in shear. When conducting the tensile test, it was found that the neoprene kept failing at the clamp point if the clamp was done up too tightly. Otherwise, if it wasn't done up too tightly, it would slip out of the clamp. In order to conduct these tests without slipping and stress concentrations, a separate fixture had to be designed. A few fixture designs were proposed to remove the stress concentrations from clamping. The first design utilizes 2 cylinders for which each piece of neoprene is wrapped around to reduce the stress concentration. Unfortunately for this design, it would almost be impossible to ensure each piece of neoprene had the exact same tension. This will cause one side to have more stress than the other and cause the joint to fail prematurely. The second design uses a single cylinder, for which one piece of neoprene is wrapped around and glued to both sides of the Kevlar. This design ensures the tension is the same in both sides. The stresses in the fixture were then modelled in FEA to determine the appropriate sizing for each component, to ensure the fixture wouldn't fail under load. Drawings were then created for this fixture and submitted for manufacturing. Both neoprene to Kevlar and neoprene to Lycra samples were created for testing. A 5mm bond line was used for each adhesive. Each adhesive was applied according to the manufacturer's directions. Some of these samples were exposed to salt water in order to test their suitability for use in the ocean. A salinity of 35 grams of salt water per litre of water was used to model the ocean's salinity. The samples were exposed for 15 days, which modelled 3 years of exposure if the wetsuit was used every third day for an hour at a time. Both the exposed and unexposed samples were tensile tested to determine their strength characteristics. 3 samples for each substrate and adhesive combination were tested. The tensile test results revealed the strength characteristics of each adhesive. Unfortunately, the Lycra samples failed in the material before they failed in the adhesive. For most of the samples, the Lycra material failed at a similar shear stress to the adhesive from the Kevlar samples. Therefore, it should be safe to use the same adhesive for both substrates. However, the Lycra in the 3M DP100 Plus failed much lower than the adhesive in the Kevlar sample. Therefore, the same conclusion cannot be drawn for this sample. After tensile testing the samples, a performance matrix was constructed to evaluate the different adhesives. Due to the time constraints, only 2 adhesives could be fatigue tested. Based on these results, 3M 5200 FC and 3M 4457 was selected for further testing. The final stage of the report involves conducting fatigue testing on the 2 best adhesives. Based on the forums, most surfers catch 10 waves per session. Based on a surfing session I had at Newcastle Beach, it took roughly 50 paddles per arm to get out the back of the break from the shoreline. It then took 20 paddles per arm to get out the back of the break after catching each wave. It took approximately 5 paddles per arm to catch each wave. Therefore, it took 55 paddles to get to the first wave, and then 25 paddles for each of the 9 waves after that. When surfing every third day for 3 years, the wetsuit experiences a total of roughly 10,000 cycles. From a previous FYP, it was found that maximum strain in the neoprene wetsuit is 0.202 in the shoulder and 0.454 in the thigh. Calculating the free length of the sample and multiplying it by the strain of the thigh results in a displacement of 18.3 mm. This value can be used to conduct a displacement-controlled fatigue test for 10,000 cycles. Even though the number of cycles is based on the movement of the shoulder, the strain value from the thigh was used in the displacement calculations to increase the safety factor of the test. Once the fatigue tests are completed, the performance matrix can be updated and the most suitable adhesive can be selected for manufacturing. Thank you for listening. If you have any questions about this project, please feel free to leave them in the comment section below and I'll do my best to address them in my poster defense. Thank you.